Every single time you transfer money, book a flight, or even just like a photo online, there's this invisible set of rules working behind the scenes to make sure things don't just fall apart. These rules are called the ACID properties, and they're basically the 4 fundamental promises your database makes to keep your data safe and sound. So let's dive in and see what they're all about.
I mean, just think about it. Imagine you're sending a friend $100. The money leaves your account, but then, right before it gets to them, your app crashes. Is that money just gone? Poof? Vanished into the digital void? What's the safety net that prevents that kind of disaster? Well, the answer is ACID.
And this whole idea really revolves around one key concept: a transaction. Now, don't let the fancy word fool you. A transaction is just a single job, even if that job has a bunch of steps. That money transfer, for instance, isn't just one action. The database has to check your balance, then it has to deduct the money, and then it has to add it to your friend's account. All of those steps get bundled up into one single logical unit of work.
So here's how we're going to break it down. First, we'll look at atomicity. That's the all-or-nothing rule. Then we'll get into the real juicy part, isolation, which is all about what different operations get to see. After that, we'll cover the big guarantees, consistency, and durability. And finally, we'll put it all together to see why the ACD test really matters.
Okay, first up is the A in ACID, and that stands for atomicity. And just like its name suggests, it means a transaction is treated like an atom, an indivisible unit. It either completes 100% all the way, or it doesn't happen at all. There's absolutely no in-between. Let's go right back to our money transfer. So before anything happens, account 1 has $1,000 and account 2 has $500. The plan is to send $100 from account 1 over to account 2. Simple enough, right?
So the transaction kicks off. Step 1, the database takes the $100 out of account 1. Now, let's just pause right there for a second. At this exact moment, account 1 has $900, but account 2 still only has $500. That $100 is floating in a kind of digital limbo.
And right at that critical moment, bam, the system crashes. Maybe the power goes out. Maybe a server just gives up. It doesn't really matter what caused it. The transaction was interrupted before it could finish the job and credit the money to account 2. So what happens to our $100 now?
This is where atomicity becomes the hero of the story. Because the whole transaction didn't finish, the database automatically performs what's called a rollback. It just undoes the change it made to account 1, putting it right back to the original $1,000. The most important thing here is that no money was ever lost. The transaction just failed as one single atomic unit, all or nothing.
All right, next up is I for isolation. And this one is huge. Databases are incredibly busy places, right? You could have thousands of transactions happening at the very same time. Isolation is the principle that makes sure all these concurrent transactions don't just trip all over each other and create total chaos. It basically defines the rules for what each transaction is allowed to see of another's work while it's in progress.
Now, when isolation isn't perfect, some really weird things can start to happen. We call these read phenomena, and I like to think of them as ghosts in the database. You might get a dirty read, where you see data that hasn't even been saved yet, or a non-repeatable read, where the same question gets you 2 different answers. Then there are phantom reads, where new data just appears out of thin air, and lost updates, where your change just gets clobbered by someone else's. Let's take a closer look at a couple of these ghosts.
So check this out. This is a classic dirty read. On the left, transaction 1 is just trying to run a simple sales report. Partway through, transaction 2 over on the right updates a sales number. Transaction 1 sees that new shiny number and calculates a total of 155. But then, oops, transaction 2 fails and has to roll back. That update never actually happened. But it's too late. Transaction 1's report is now just wrong because it was based on dirty, uncommitted data.
A really simple way to think about it is this. A dirty read is like quoting a sentence from a rough draft of a document that you're peeking at over someone's shoulder, right before the author decides, nah, I don't like that, and deletes the whole section. Your quote is now based on something that, for all intents and purposes, never existed.
Okay, here's another ghost for you, the phantom read. Transaction 1 asks for the total sales and gets, say, 130. A moment later, transaction 2 adds a brand new sale and successfully saves it. Now, when transaction 1 runs the exact same query again, it gets a different answer, 140. A new phantom row just mysteriously appeared out of nowhere, making the whole report inconsistent.
It's that weird feeling of rereading a page in a book, only to find that somebody snuck in and added a whole new paragraph since you last looked. It's confusing, right? It totally breaks the flow. And that's exactly what a phantom read does inside a transaction.
So how do databases actually fight these ghosts? Well, there are two main strategies. The first is pessimistic control. That's the better safe than sorry approach. It locks down data to prevent conflicts before they can even happen. The other is optimistic control. This is more of an easier to ask for forgiveness than permission approach. It just assumes conflicts are rare and only checks for them at the very end. It's way faster, but it runs the risk of having to fail and retry if a conflict did actually happen.
Now this slide. This is the ultimate cheat sheet for understanding all of this. It perfectly shows the trade-offs. On the left, you've got the different isolation levels. See read uncommitted at the top? That's the fastest. But as you go across the row, you can see it allows all those spooky read phenomena to happen. As you move down the list to read committed, repeatable read, and finally the strictest one, serializable, you prevent more and more of these ghosts. But, and this is the key, that extra protection usually comes with a performance cost. Choosing the right level is a critical balancing act for any developer. All right, on to our final two letters, C for consistency and D for durability. So, if atomicity is about the transaction succeeding or failing as one piece, and isolation is about transactions not messing with each other, then consistency and durability are all about protecting the integrity of the data itself.
Let's talk consistency first. All this means is that any transaction has to take the database from one valid state to another. It always has to follow the rules. For instance, let's say we have a table of pictures that only has IDs 1 and 2. This other table here shows who has liked each picture. Now, a pretty basic rule for our app might be that you can only like a picture that actually exists. So, looking at this data, can you spot the one entry that's breaking that rule?
Did you get it? Yep, it's that last row. Edmund apparently likes picture ID 4, but we already know that only pictures 1 and 2 exist. This is what we call an invalid state. A database that enforces consistency would simply reject this transaction, protecting the logical sanity of our data.
And finally, we have D for durability. And this is probably the most straightforward promise of them all. It simply means that once the database gives you the thumbs up and says a transaction is committed, that data is safe, period. It's been written to something permanent, like a hard drive, and it's going to survive a power outage, a system crash, anything. That's the guarantee.
So that's the whole shebang. Atomicity, isolation, consistency, and durability. ACID. Together, these four principles form the absolute bedrock of how we reliably manage data in almost every system we use.
And if there's one thing to take away from all this, it's that the ACID properties give us incredibly powerful guarantees about our data. But as we saw with those isolation levels, these guarantees aren't free. There's always a trade-off to be made between how strict these safety rules are and how fast the system can perform. And that really leaves us with a final and pretty tough question. In a world that demands every app be faster and more responsive than the last, which of these guarantees would you be willing to relax to gain a little more speed? Would you risk a few dirty reads to make a social media feed load instantly? Would you trade a little bit of durability for faster writes? The answers to these questions are what define the architecture of the entire digital world we're building.